All right, so I'll try to talk loud. Hopefully the audio is okay and pretty clear. I'm going to do some more examples of Bayes' theorem. So the first one we have here is, let's assume that we have some truth theorem that can make someone say whether or not they're guilty or innocent. All right? So we're given the following information, that given that someone is innocent, the probability this truth theorem makes them say they're actually guilty happens about 0.01 or 1% of the time. Given that someone is guilty, the probability this truth theorem, incorrectly doesn't work, and that they can still say they're innocent, is about 0.1 or 10% of the time. If we assume that all suspects that are brought in and given this truth theorem, that 5% of them are guilty. And then the next thing we want to know is, if the truth theorem indicates they're guilty, what's the probability that they're actually innocent? So how do we approach a problem like this? So the very first thing I'm going to do is write down what information we're given, and then whether or not, and then kind of the second thing is, what are we actually looking for? So I've got a whiteboard here. Hopefully I can write. You can kind of see it large enough. But we were told that the probability that given that someone is guilty, the truth theorem makes them say they're guilty. I'm going to shorthand this too. This was told to us to be what? Truth theorem makes them say they're innocent. This was told to us to be 0.1. The probability that the truth theorem makes them say they're guilty, given that they actually are innocent, was 0.01. Okay? So we could start to build and then we were just told in general, the probability that someone is guilty, if they're a suspect brought in, is 0.05. Okay? So I'm going to start to build my tree, right? Here I've got the probability that they are guilty is 0.05. Probability that they're innocent would then be, well, we know we have two states of nature. They have to add up to 1. And so this probability, if the probability that they're guilty is 0.05, the probability they're innocent is 0.95. Okay? From there, we'll create this other branch. And we're going to be looking for two different probabilities. Okay? The first probability is that given the person is guilty, what's the probability that the truth theorem makes them say they're guilty? And then given that they're guilty, what's the probability the truth theorem makes them say they're innocent? Right? That's what we're going to be looking for. Now, we were given one of these. I believe this is the one that we were given up here. So this is 0.1. We know that these have to add up to 1. So if this is 0.1, this one has to be 0.9. We do the same thing over here on the other tree, on the other side. It's just now we'd be looking for the same outcomes of the test, but we would be conditioning on whether or not someone's innocent. Right? So that's how we would start kind of to put everything together, all the information that we have. Now, I only did this side because I knew that that's going to be the only information we need to solve this problem, but we could do this other side as well. Need my eraser here. So just to kind of give myself a little bit more room, I'll rewrite that in a second. So here we want to find two probabilities. Both of them will condition on the state of nature of the side of the tree we're on. So given that someone's innocent, and here we'll say the probability the truth theorem makes them say they're guilty, truth theorem makes them say they're innocent. Now we were given one of these. If we go up here, given that someone's innocent, the probability they say they're guilty is 0.01. We know that these have to add up to 1, so this one would just be 0.99. Okay? So if we have the other branch, and then in this branch, it didn't have a whole lot of room. I probably could have organized a little better. We need to have all the information we need to answer any question. So if we go back here, and we just write down what we were given, right? These were the two things we were given. We knew the probability that someone's guilty is 0.05, which allowed us to find the probability that they're innocent is 0.95. And then we also got some additional probabilities building that tree. And I'll show you how we would do it even if we didn't build the tree in a second. So what are we looking for? Well, the question was, given that the truth theorem indicates that they're guilty, and once again, on an exam or something, I'd write the word given in here, what's the probability they're actually innocent? So we're saying, okay, given that I see the truth theorem come back saying guilty, what's the probability they're actually innocent? So what I'm going to do is I'm going to say, okay, this is my state of nature. This is the outcome of my test. So this is E, this is S1. I'm going to go back, just like we did for our example in class today. I'm going to look at this equation and say, okay, my E was that the truth theorem made them say they're guilty. So everywhere there's an E, put in truth theorem made them say they're guilty. My state of nature that I'm interested in is, are they actually innocent? Everywhere there's an S1, put in innocent. And now S2, state of nature 2, well, the first state of nature is that someone's innocent. The second state of nature is that they're guilty. Okay? So I'm just going to write that out in the context of my example. Oops. So here we go. So I just wrote everything out. I have everything written out in the context of my example. It's very easy to find the probability someone's innocent. Given they're innocent, the probability that the truth theorem made them say they're guilty, 0.01. So we plug that in, 0.95, 0.01, 0.95, 0.01. The probability someone's guilty is 0.05. Now the last thing we need, we weren't directly given, right? But when we built that first branch of the tree, we actually found this probability. So remember, if we condition on the same state of nature, so we're saying, look, assume someone is guilty. If they are guilty, then the truth theorem makes them say they're innocent with a probability of 0.1, which would mean the probability that guilty person says they're guilty with a truth theorem would just be whatever gets us up to 1 or 0.9, right? And that's because when we condition on the same state of nature, the two outcomes of the test, the conditional probabilities have to add up to 1. Right? And if we would have had the tree built, we would have been able to see that as well. We would have already had that piece of information, and we would have just been able to just plug it in. Right? So very similar to what we did in class, just a little bit different, right? So we can kind of plug our numbers in. We get about 0.174. Okay. So given that the truth theorem makes them say they're guilty, the probability someone's actually innocent is about 0.174. All right. Now, if we have that information, we also know we could actually answer a different question as well. So I'm going to write this out in here in just a second. So let's say what I just found was the probability that given the truth theorem makes them say they're guilty, the probability they're actually innocent was 0.174. What if I wanted the probability that given the truth theorem makes them say they're guilty, what's the probability they actually are guilty? Well, notice it's kind of similar to when we condition on the same state of nature. It's just now we've conditioned on the same outcome for the test. But if I'm saying, look, assume this person said they're guilty because of the truth theorem, the probability they're actually innocent is 0.174. Well, the only other thing they could be other than innocent is guilty. And so the probability that they're guilty, conditioning on that same thing, well, these two things would just have to add up to 1. And so I know that if the probability that they are innocent given this outcome of the test, the probability that they're actually guilty would just be 1 minus that, or 0.826. Now I could go through and rewrite this, use this as my E and this is my S1, and then I could just rewrite out Bayes' theorem, and I could, go through a much longer process, and I'd still find 0.826. It just, with the information that we had already found, there's a kind of a shortcut there because we're conditioning on the same thing. The two different conditional states of nature would have to add up to 1. Right? Or the probabilities of the states of conditional probabilities of the states of nature would have to add up to 1. So if I asked you a question here, given that the truth theorem makes them say they're guilty, what's the probability that they are actually guilty? Well, that's what I just showed you on the board, right? Given that the true serum makes them say they're guilty, what's the probability they're actually guilty, right? And we know that we could walk through the whole process or use what we found earlier and find that that's 0.826, okay? So, this is kind of interesting. We think about like juries and truth, and instead of this true serum, replace it with like a jury. Oh, sorry. Then we could actually think about, okay, instead of a true serum, we have a jury. So given that someone's guilty, what's the probability a jury actually finds them innocent? Given that someone's innocent, what's the probability the jury finds them guilty? And if we wanted to know, what's the probability that someone who's in jail right now is innocent? Well, if they're in jail, they were found guilty by a jury. So we're saying, given that they were found guilty, what's the probability they're actually innocent? And here, this photo was supposed to line up with this first guy. Second photo is supposed to line up here, right? Someone who's guilty, but the jury found him innocent. Here, someone who's innocent, jury found him guilty. And you could maybe you don't believe this if you ever seen Making a Murder, but that was kind of my example there. Well, the interesting thing about this is if I wanted to find the probability that someone's in prison who's actually innocent right now, I can get some of these other conditional probabilities, like what's the probability that if someone's innocent, a jury actually found them guilty? Well, it's kind of hard to know because we never really know the underlying true state of nature. But using things like DNA reversals, right? Like before and after DNA, we can start to get an idea about how many juries actually found people guilty even though they were in fact innocent. And how many, times did the jury actually get it correct and find a guilty person guilty, et cetera, et cetera. So if we can use some of that like past data on kind of DNA reversals, we could actually probably get a pretty good idea about what the probability of people in jail are that are actually innocent. All right? So, this Bayes' theorem has some real has some real useful real-world applications, and it's useful, and that's why we're kind of going through it. So the other thing I would do, and I'm kind of doing this one on the fly, but I think it'd be a somewhat interesting example. So let me see. I'm going to Google search COVID false positive rate. I think this was the one that I was looking at earlier. Yeah, so here we've got some information. So probably a little bit small, but you're going to have to kind of trust me, and I'll start to kind of write this stuff down for us. All right? So let's say what we're interested in, and we'll think about this in a couple different ways. So let's say I want to know, given that I see a positive test result on a COVID test, what's the probability the person actually has COVID, right? So given that the test comes back positive, what's the probability that the person actually has COVID, right? So this is my S, this is my E. Right? I would then have to rewrite this in the context of Bayes' equation. So if I look at Bayes' theorem and wrote this out in the context of my example, the first thing would be take the probability of the first state of nature, so COVID positive, times the probability of E, test comes back positive, given they actually have COVID. Now the first part of our denominator is the exact same thing, so I might write this a little bit smaller, just so I leave myself some room. Then you'll add to that the probability of the second state of nature, which is that, and I'll get out of the way in a second, that they're COVID negative, times the probability of the outcome of the test we're interested in, given that second state of nature. Okay? So now we just have to work on finding these probabilities. So the very first thing is, what's just the general percent of the population that has COVID at any one point in time? So let's look. Let's look at this. So we've got different percentages here. Looks like they're all right around 5%, so let's just use 5% for that, okay? So I'm going to say the probability that if I selected a person at random that they have COVID is about 5%, right? So everywhere I see COVID positive, I could plug in 5%, which would also mean the probability that someone chosen at random is negative for COVID is 0.95. Now the other thing I'm going to need is, given that they're COVID positive, what's the probability I see a positive test result, right? So if I go here and look at my other source, it says, I'm thinking about people that have the disease who actually get a positive result. Well, here it's telling me people that have the disease, where is it? False negative, right? And get a negative result is pretty wide range, right? So when I'm told, I was told this by when I got mine, I was told it's as high, I was told it's like 30%, right? I'm not going to read this whole thing. So let's just take kind of the middle range here. Let's use 20%, okay? So that was telling us, given that they are HIV positive, the probability they actually get a negative test result is about 0.20, which would mean the probability that they get someone that has HIV actually gets a positive, HIV, that probably that someone that has COVID actually tests positive is 0.80. Now the other thing that we don't have yet is, given that they're COVID negative, what's the probability that a test comes back positive, right? So if I look here, this says that it's 5% or lower. We'll use the highest amount, which is 5%. Right, so 0.05. And now I have everything I need to find what I originally wanted, right? So I'm just going to plug all these values in and then kind of use my calculator or Excel. So I'm actually going to pull up Excel here so I can see this. Actually, might just be easier for you guys. I'll just write this on the board. We'll kind of plug all these values in, right? So the probability that someone has COVID, any one person at random, is 0.05, 0.05. Probability they are COVID negative, 0.95. Given that they have COVID, the probability they get a positive test result right here, 0.8 and 0.8. Given that they don't have COVID, the probability they get a positive test result, 0.05. Okay? So I now have all the values. It's just a matter of kind of plugging away and getting this entered into my calculator. So with that in mind, let's see what it actually is. Let's go to Zoom here so you guys can see this a little bit easier. So it was on our numerator, we had 0.05 times 0.8 divided by 0.05 times 0.8. And these are just numbers I'm grabbing. If you go back and look at the board, these were the numbers that I had written on the board. This was not the number I had written on the board. There we go. So we get about 45%, right? So given that somebody gets a positive test result, the probability they actually have, if they told you, I have a positive test result, the probability they actually had COVID, if we made every single person get tested, would only be about 45%, right? And it's similar to when we talked about the HIV example today, and it's that, well, look, the probability you actually have is so much lower that you don't. If we tested everybody, these false positives end up being quite a large number of people, right? And so we're going to have way more, these underlying these probabilities, we can also think about them as frequencies. And so you're going to have way more people that have false positives in terms of the number of people, because there's just more people that don't have the disease. So this is kind of a fun example, where we can take Bayes' theorem, write it out in the context of our example. We can look for these different probabilities that we don't have. Like I just grabbed those from some Google searching and looking at some of the medical kind of literature that's out there. Now, I don't know how accurate these numbers might be a little off, but I doubt they're too far off. That was like a pretty reputable, right? What was this? Harvard Health Published Medical School. Like I'm gonna kind of believe them, right? Like it's a pretty, and then the CDC was the one that we used for this. So, you know, kind of a fun example of Bayes' theorem. Just a couple more examples, get some practice with it. We'll start with discrete random variables on Monday, and hopefully this kind of helped give you some more examples, a better idea about how we would solve some of these problems using Bayes' theorem.